We're going to find the volume of the solid torus with radius little r and radius big R. What's going on is you have this torus. It seems like they want us to the circle and kind of go around the axis like this, add up all the little disks, right? And you get your volume. That's a trap. That is not how you do it. What you want to do is you want to think of this torus like a bagel. And you want to look at it from the top. Look at it like that picture right there. And the way this picture is right here, right, would be like this picture. And what you want to do is you want to take the top off the bagel, and you want to kind of think of a slice of the bagel. So we're looking at this picture right now. Looking at it from the top, and they're saying that we have big R, which kind of goes to right there, and then little r, which goes out right there. And now, let me bring your attention to this other drawing over here. This right here is our bagel slice. And notice there's still two radii, right? It's capital R, but it goes from there to there. And then you have another circle, an outer circle, that's determined by this radius right here. How would you find the area of a circle, or like a washer? If you had a washer, from here to here is R. Just from here to here is little r. You want to use this circle that has a radius of big R plus little r, and you want to get the area of this big circle. Then you want to subtract out the area of the hole, like that circle there. And by doing that, you would get the area of the ring, which is right here, right, the area of the washer. Okay, and if we could get the area of that washer, and we added up all those little slices, then we would have, you know, from the bottom to the top, so that slice there, slice there, slice there, slice there, slice there, slice, slice. We add up all those slices, all right, with thickness dy. We added up all those volumes of those slices, then we would have the volume of this torus. So you could think of this slice right here. You can think of the slice as a little cylinder, except it has a hole in it. You need to use this method that we talked about up here to get the area of the ring, that washer. Subtract the big radius, just get the bigger circle minus the smaller circle, get those areas. The area of the big circle minus the area of the small circle. That gets you the area of the washer. So let me write that down. Area of bagel washer equals area of big circle minus the area of the small circle, which is kind of like the area of the hole. Area of small circle. If we did that, we get the area of the bagel slice. Volume of the bagel slice. That's equal to, same thing, area of the big circle times the height, the thickness of the slice. Okay, area of big circle minus area of small circle times dy, which is the height of the bagel, or the height of the slice. So we'll call the height of the slice right here dy, or call this right here dy. How do we get the area of the big circle and the area of the small circle? Well, we know that area is pi r squared. Right? So first of all, let's get our two radii, because it might not be clear. First radius, to get the radius of the outer circle, area of the big circle, which is right here, area of the big circle would be pi times the radius. Radius actually isn't big R, right? Because it's not just big R, it's big R plus little r. That gets you all the way from here, all the way to the edge there. From here, all the way to the edge there. So it's going to be big R plus little r, pi r squared. Area of the small slice minus area of the small slice. Well, big R is too big. I mean, it goes beyond, small circle, area of the small circle. It goes beyond our circle, right? We want our circle to stop at the hole. We have R, then we need to back it up by little r. So big R minus little r becomes the radius of the hole. So pi big R minus little r. And then you multiply that by dy, you got yourself volume of your slice. But we have a problem. Problem is that we want to add up all our slices. We want to add up the volume of that slice down there, and then the one that's a little bigger that's on top, and the one up there, and up there, 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 there. And if you notice, the radii aren't going to be the same. Think of a bagel. I could cut a slice on this bagel, and it'll be smaller than this slice, right? You just cut closer to the bottom, you got a smaller slice. If you cut like in the middle, you're going to have your biggest possible slice. But as you go higher up, now you got a smaller slice again, right? So like that slice up there should be smaller than the slice there, right? And then as you get closer to the top, smaller. The radius keeps changing, and we want to be able to add up all our little slices all along the y-axis. We want to add up the volumes of all your slices. So how do we account for this dynamically changing slice? What you want to do is you want to think about this circle that's right here. If you think about this big R is the same throughout. That's one thing that's consistent, right? The big R is the same no matter where you are in your slice. Little r changes. Little r is going to change depending on the slice. It's not that little r, the length itself is going to change. Its coordinate is going to change. It's still going to have the length of little r, but its coordinates are changing depending on where you are and the position of little r. You know, whether it's there, or there, or there, or there. Its coordinate, its location is going to determine whether your slice is wide, less wide, or more wide, or back to less wide again. All right, so we need a formula that has that changing little r value, right? That dynamically changing little I coordinate that kind of goes around the circle with us. So as we're integrating from the bottom to the top, a little r is changing with us. Those coordinates are changing with us, increasing or decreasing the distance as we go up the top. So our little volumes that we're taking along the way represent that change. So we need two equations of a circle. One circle will represent the whole, and the other circle will represent the outer rim. We'll get the area of the outer one, subtract the area of a smaller one, and we're in business. So one more time. We have our whole, we have this right here. What we want to do is we want to find an equation that gets us to right there. And we want an equation that allows us to get this circle. So we want an equation that maps kind of this circle and the one that maps this circle. And then we can use this kind of idea of the bigger circle, area of the bigger circle minus the area of the smaller circle, based on this like dynamically changing radius determined by this r right here. All right, so let's get the area for this outer circle. So let's get the location of this outer circle. So the key to finding these lengths and having them dynamically change is going to be related to this circle that's right here. What you want to do first, you want to get an equation for this circle. This equation for the circle will map any x value along the circle. Well, the equation for any circle is x minus h squared plus y minus k squared equals r squared. All right, so that's the generic equation of a circle. And the center would be located at h comma k. The center of the circle basically is located right here at r comma 0. R along the x-axis and 0 along the y-axis. And the center is h comma k. So it's going to be the opposite sign since there's minuses. So it's going to be x minus r squared plus y minus 0 squared equals r squared. We're going to use the same r. That's the radius of the little circle. So that's the translated equation of a circle with radius r, and its center is located at r comma 0. And you don't need to have this 0 right here, because anything minus 0 is just the thing before that. We can just write this as y. We write this down below. So we have x minus r squared plus y squared equals r squared. So far we have not mapped anything on this circle or on this circle, right? We have not mapped anything on this circle here, right? Or the inner one. We haven't done anything there. We haven't done anything here. All we've done is we found an equation for this circle right here. But the equation of this circle right here will give us any point along this circle. And we can kind of use that to get an equation of the other two circles. Will help us determine the radii for the other two circles that we can use to make areas that we can subtract, and those areas would vary as you go from the bottom to the top because the values change along the path of this curved circle right here. If you take your slice up here, for example, your slice would be here, and it would be less wide than the slice here. But we're going to have an equation that'll take that into account and help us get the area of that slice, or the area of this slice, or the area of any slice as you go from top to bottom. Let's think about this. We know that this is the formula for the little circle that we're doing, the one that's perpendicular to the slice of the bagel, right? So this is the formula for this circle right here. Let's solve for x. So we're going to do that by moving y to both sides. Minus y squared minus y squared. You're going to get x minus r squared, well, that's gone, equals r squared minus y squared. Now let's go ahead and square root both sides. Root plus or minus root. Okay, so this root right here is going to take care of that square right there. So they'll kill each other. So you end up with x minus r equals plus or minus square root of r squared minus y squared. Then we can move this little r over here, plus r plus big R, and you're going to get x equals big R plus or minus the square root of little r squared minus y squared. Notice that this equation here is in terms of y. Solve for x in terms of y. So that means that what we've done basically is, instead of having a circle that kind of maps like this, usually when you solve for y in terms of x, your plus or minus kind of represents the top half and the bottom half of a circle. Well, in this case, our plus or minus is representing the side halves of the circle. One's going to be this half of the circle. That would be the plus one. So that will be your r, would get you to here. And plus this other little piece right here, which would be this guy right here, the square root of r squared minus y squared. And you see how that's kind of dependent on this y value right here. So it's going to kind of change according to where you are on the y-axis, right? So sometimes it'll be bigger, but sometimes it'll be smaller, right? So if you were up here, for example, this r would be the same, then this distance would be smaller. This r would be the same, this distance would be smaller. We have that one. The minus, well, the minus will get us to this side of it, or to other side of it, which is right here. Right? So you have r, which is this all the way here, minus the square root of r squared minus y squared would get you then the distance from here, from the origin here, right? So depending on your y value, lower y value, there, higher y value, there, right? So now you have two equations, one getting you to this side, and one getting you to this side. Now we're able to get all the way to here, right? And then we can take the area of this big slice. Anywhere along the y-axis we go, it'll keep changing, whether it's a big slice or a smaller slice towards the bottom or a smaller slice towards the top. And we also were able to get the area of this hole now, because it'll be determined by this radius. Well, let's split them up. So we have x equals r plus the square root of r squared minus y squared, and the other one is x equals r minus the square root of r squared minus y squared. Let's just use this formula now, right here and right here. And let's put the dy in there as well, because we're going to get the volume of the slice. All right, so I'm just going to copy this down, just like I see it. So for here we have volume of slice, just one slice, equals pi big R, this one, squared minus. No, this is supposed to be the radius, right? So we're going to do the big radius. So instead of big R plus just regular R, we're going to do big R, which is right here, plus dynamically changing R around the path of the circle. Big R, so big R plus root R squared minus y squared, minus pi times big R again, minus dynamically changing radius that would allow us to get the area of the hole, r squared minus y squared, times dy, which is the height of the bagel slice. Remember, so it's kind of like we're doing a cylinder. We got our base area, we got our height, but the volume of the cylinder. Now we're going to add up all the cylinders, right? So we're going to add up all the slices from the bottom, here, add them from down here all the way up there, and that'll give us the total volume of our torus. We are going from lowest possible value, negative r, down here. Negative r is as low as we're going to go on the y, and positive r is the highest we're going to go on y. And if you ever get confused on your limits of integration or your boundaries, you can just think of it as the lowest part your slice can travel to the highest part your slice can travel. So the slice can't go down here. The slice is going to start right here and then work its way and then go all the way up. So in this case, negative r is the tabletop and then work its way all the way up. All right, so we're going to go from negative r to r, positive r. All right, and then it's this exact same formula right here. Pi times the quantity of r plus the square root r squared minus y squared closed. That's the big area of the bread and the hole combined, minus pi and then r minus root r squared minus y squared. That's just the area of the hole. And don't forget, this is all going to be with respect to dy. So this is going to involve some major simplifying. First thing we can do is we can factor out a pi. Pi is a constant, you can take it right out of the integral, right? So pi comes right out. All right, so we're still going from negative r, went from negative r to r, positive r. Pi's are gone, now we have big R plus root r squared minus y squared, whole thing squared, minus big R minus root r squared minus y squared, close, squared, dy. Now we got to do a massive foil explosion on this thing. Here we go. Pi going from negative r, positive r of, okay, so here goes. Let's write it over here on the top. So we have r plus root r squared minus y squared. Put them side by side. R plus root r squared minus y squared. So this is what we have there. I did it 2 times because we're squaring it. Put it over here. Now we're going to FOIL it. All right, so we do our first. Our first is r squared. We do our outside plus r times the square root of r squared minus y squared. All right, so we got our first, got our outside, got our inside, which is right here, which is plus r times the square root of r squared minus y squared. All right, and then we do our last, which is, or just that guy and that guy. All right, well, that's just, if you're multiplying two things that are exactly the same, they have the root on them, you just take the root off, right? Just like the square root of a times the square root of a, it's just a. All right, so root comes off. So we have, and it's positive, so it's going to be positive r squared minus y squared. All right, that's our last. So we got our first, our outside, our inside, our left. Minus the same thing again, except this time big R minus the square root of R squared minus Y squared. Let's go ahead and just change this right here to minus, right? Minus, minus. Do our first. First is R squared. Outside, negative R times the square root of R squared minus Y squared. Inside, right here. So negative, right, times a positive. So minus R times the square root of R squared minus Y squared. And our last, which is that times that, which is a negative times a negative, which is a positive. Once again, a root times a root, just take the hat off the root. So it's going to be R squared minus Y squared. Close the bracket. There's our FOIL explosion. Next thing we're going to do, distribute this invisible negative 1 right here. We're going to do that. Before we do that, the smarter thing to do would be to collect our like terms, right? So we can hook those guys up and we can hook those guys up. Put down here, pi negative R to R of big R squared plus these guys together. It's just 2R root R squared minus Y squared plus R squared minus Y squared minus bracket R squared. Hook these guys up right here. All right, so minus 2 big R root R squared minus Y squared plus R squared minus Y squared. Close bracket. Now pi negative R, positive R, basically copying this whole thing down from the top, right? So I'm not changing anything right now. Just rewriting the top again. R squared minus Y squared plus R squared minus Y squared. And then I'm going to distribute the invisible negative 1 that's right here. Go like that, and like that. All right, so basically opposite sign everything on the inside. So I'm going to get minus big R squared positive 2R root R squared minus Y squared minus little r squared minus Y squared. Now we have some simplifying we can do. The big R squares wipe out. Gone, gone. So this is positive R squared, negative R squared. Great. That's still negative, but you have to distribute. Extend your distribution over here. Make that opposite sign, making this positive. All right. Now they should wipe. So you have positive R squared wiping with negative little r squared. Negative Y squared wiping with positive Y squared. What's left? What's left is you have this and you have this. Everything else y. You can combine those. So now you have the integral of negative r pi. Put those together, so you're going to get 4 big R root R squared minus Y squared. And this whole time there should have been a dy. Now we're going to take the 4 right out. 4 comes right out. 4 pi integral negative R positive R, and right here R squared minus Y squared. And don't forget there's dy's along the way. Dy's along the way. All right, the next part is a bit of a trick. So this guy right here is kind of the equation of a circle. Let's think about this basic equation of a circle. X squared plus Y squared equals R squared. If we isolate X squared, right, so we're going to go minus Y squared minus Y squared minus Y squared. Then you're going to get X squared equals R squared minus Y squared. Then take the root of both sides, root plus or minus root. Then you end up with x equals plus or minus the square root of r squared minus y squared. And if you notice, this right here, it's a lot like this right here. So if we graph this circle, it's a circle centered at the origin, right? This is the equation of a circle centered at the origin, because x plus 0 squared plus y plus 0 squared equals r squared, where 0 comma 0 is the center of the circle, because the center of the circle is h comma k, centers the origin, right? So we have a circle centered at the origin, has nothing to do with any of the stuff that we did. This is not like any of these circles, it's just a circle. Got our circle right here. We're going to go ahead and say, all right, well, this is the radius of the circle. So this radius is r, because, you know, it says r, and we do go like this. That's the equation of this circle. But now when you split it up like this, you do in terms of x, like we talked about earlier, you're getting 2 halves. You're getting the equation of, because it's x in terms of y, you're getting the equation of the right half, and you're getting the equation of the left half. That's why you have your plus or minus. If we look over here, it doesn't say plus or minus. It just says plus. Okay, so I'm going to get rid of the minus. That gives us x equals just plus the square root of r squared minus x squared. Okay, well that means now we have this right here. And the coordinates right here, because it's the radius, is r, right? And this is also r as well. And since we're going with respect to y, well, let's think of it if it was in terms of x. So if we had this exact same thing, right? And there was an x right here, and there was an x right here, right? Then it would be this type of thing. It would be a graph like this. And when you're integrating, you're finding the area under the curve. That's what integration does, right? So if I go from negative r to positive r, I'm getting the area under the curve. But in our example, we're not going with respect to x, we're going with respect to y. We got to see it from going from here to here, right? And it is the area to the right of the y-axis. There. That's all that means, right? So instead of going from left to right, you're going from bottom to top. And since this is positive, it's up here. We're just getting the area of a half a circle. So all this means right here, that literally means area of half circle. So we can go to our 6th grade skills right here and not integrate this. Just get the same result. Area of the half circle. Well, it doesn't matter. It's a circle, right? So it doesn't matter how you do it. But the circle, it's an area of a half circle with radius r. All right, well, I know the area of a circle is area is equal to pi r squared with radius r. That means the area of a half circle is the area of half circle is 1/2 pi r squared. Therefore, all of this stuff that's in here, when it's all said and done, is 1/2 pi r squared, which is the area of that circle over there, which has nothing to do with this problem, besides the fact that it's a cute little way of not doing some sort of crazy integration over here. We go over here, and we say, all right, well then 4 pi times the area of my half circle, which is that, right? So 4 pi times 1/2 pi r squared equals 4 times 1/2 is 2, right? So 2 pi squared r squared. Oh, and somewhere along the way, I lost my big R. Look, there it is. It's big R is a constant. See, it's just magically disappeared over here. So it should have came out right here. It goes along for the ride with pi. Big R is right here. So then you have your big R is right here. So it's 2 times. So 4 times 1/2 is still 2. You have your big R, check. Pi squared, check. Little r squared. And there you go. So this is the volume of the torus.